Founded in northern Italy, Lucchini Mame has spent decades refining the art and science of large-scale forging. Their facility handles steel billets that can weigh several tons, heating them to temperatures exceeding 200 degrees Fahrenheit. Hot enough that the metal glows a brilliant orange-white and becomes workable under extreme mechanical force. The process begins in the furnace. Large steel ingots are carefully heated for hours to ensure a uniform temperature throughout the entire cross-section. Because uneven heating leads to weak spots, and in a crankshaft, that's simply not acceptable. These aren't components for lawnmowers. We're talking about crankshafts destined for massive ship engines, industrial generators, and heavy-duty machinery. Once at temperature, the glowing billet is moved, often by overhead cranes, to a hydraulic forging press, and these presses are no joke. Lucchini Mame operates forging equipment capable of delivering tens of thousands of tons of force, shaping the steel through a series of controlled blows and compressions. Each step of the forging sequence is carefully planned to align the grain structure of the metal, giving the finished crankshaft incredible strength and fatigue resistance that simply cannot be achieved through casting alone. After rough forging, the part moves through trimming, which removes excess flash, those irregular edges formed during the pressing operation. Then comes normalization, a heat treatment process where the forging is reheated and slowly cooled to relieve internal stresses and refine the grain. The result? A tough, dimensionally stable blank, ready for precision machining. Now, if you've ever watched a master craftsman whittle a piece of wood down to something perfect, you already understand the soul of what's happening here. Except this time, we're talking about steel. Cold, hard, 2,000-pound steel. This is the Haas Street 55, one of the most powerful CNC turning centers ever built. With a swing of over 30 inches and a between-centers length that handles massive workpieces, this machine was built for jobs that would stop most lathes cold. We start with a rough billet, 2,000 pounds of raw steel, and right out of the gate, we're not tiptoeing around. The first passes are aggressive roughing cuts, 0.25 inches deep, with a feed rate of 0.025 inches per revolution. The chips flying off that tool aren't shavings, they're chunks. But here's what's really impressive. Even when we shift to those curved profile surfaces, the tool doesn't slow down. We're running a 0.112-inch feed along oscillating toolpaths, cutting at 0.050 inches per revolution. That's the Haas Street 55 doing what it does best, staying efficient even on complex geometry. By the time this part is finished and lifted off the chuck, we've removed over 800 pounds of steel. What's left is a precision component shaped exactly to spec. Proof that modern CNC turning isn't just machining, it's sculpture, done at industrial scale. There's something almost timeless about a pressure vessel. Whether it's holding natural gas, industrial chemicals, or compressed air, these cylindrical steel tanks have been the backbone of American industry for over a century. And the folks at TIG Corporation are keeping that tradition alive with some serious modern muscle behind it. TIG is a Pennsylvania-based manufacturer that specializes in custom-fabricated steel tanks and pressure vessels. What sets them apart isn't just their equipment, it's their process. Every vessel starts as flat steel plate, sourced and certified to ASME standards, which means it's been tested and verified to handle the pressures it'll face in the real world. The first step is plate preparation. Steel sheets are cut to precise dimensions using plasma or laser cutting systems, then rolled through a plate rolling machine, a 3-roll or 4-roll hydraulic bending system that gradually curves the flat plate into a perfect cylinder. Getting the roundness right here is critical. Even a slight deviation can cause stress concentrations that compromise the vessel down the line. Once the shell is formed, the longitudinal seam is welded using submerged arc welding or SAW, a process where the arc is hidden beneath a layer of flux, producing deep, clean welds with almost no spatter. This isn't your backyard MIG welding. SAW delivers weld quality that meets pressure vessel codes like ASME Section 8. Next come the heads, the domed or flat end caps that seal the cylinder. These are either purchased as pre-formed flanged and dished heads, or pressed in-house using hydraulic forming equipment. They're fitted to the shell and welded with the same precision. Throughout the process, non-destructive testing, NDT, is carried out, radiographic testing, ultrasonic inspection, and hydrostatic pressure testing to make sure every weld and every seam is exactly where it needs to be, holding exactly what it's supposed to hold. What comes out the other end is more than just a tank. It's a certified, engineered pressure vessel ready to be put to work in refineries, water treatment plants, and chemical processing facilities across the country. Old-school craftsmanship, backed by modern engineering, that's TIGG. When a cargo ship the size of a city block needs to move through open ocean, it relies on something most of us never think about: the propulsion system buried deep in its hull. And one of the companies building those systems is Wärtsilä, a Finnish industrial giant with manufacturing operations right here in China. At Wärtsilä's Chinese facility, the production of marine propulsion systems is a tightly choreographed process. Massive engine components, crankshafts, cylinder blocks, camshafts, are machined to tolerances measured in microns. Assembly lines run with a precision that would feel right at home in an aerospace facility. These engines aren't just powerful. They're engineered for fuel efficiency and low emissions, because in today's shipping industry, every gram of fuel counts. Wärtsilä's work here is a reminder that some of the most impressive manufacturing on the planet happens far from the spotlight. Before you throw something away, ask yourself, could it be rewound? That might sound like an odd question, but at Koffler Electric, it's the question they ask every single day. Because here, dead motors don't get scrapped. They get reborn. Motor rewinding is one of those trades that's been around since the early days of electrification, and Koffler has turned it into an art form. The work begins with a complete teardown, stripping old, burned-out windings from the stator cores and rotor assemblies, and from there, the skilled winders get to work. What you're watching in this clip is a masterclass in electromagnetic craftsmanship. The team performs random winding of multi-strand stator coils, a technique where insulated copper conductors are carefully layered into stator slots without a fixed pattern, maximizing fill factor and efficiency. For the rotating field coils, they switch to layer winding, where each turn is placed with deliberate precision to control inductance and reduce heat buildup. Then there's the random wound AC exciter rotor, a spinning assembly that generates the field current for synchronous generators. Getting this right requires not just skill, but a deep understanding of electromagnetic balance. But the real showstopper in this video: the lamination replacement sequence on a 500 kilowatts generator. Replacing the stator laminations, those thin silicon steel sheets stacked inside the stator core, is painstaking work. Each sheet must be precisely restacked, insulated, and compressed to restore the magnetic efficiency of the original design. We also see the commutator undercutting sequence, where a laser-guided tool is used on a large rotor to trim the mica insulation between commutator segments. Too little, and the brushes won't seat right. Too much, and you've damaged the commutator. It's a job where precision is everything. The finale? A 5000 kW generator output voltage test. Watching the meters on all three phases climb and balance tells the story better than any words can. When those readings line up perfectly, you know the rewind worked. A machine that was dead is alive again, and that never gets old. Now here's something that'll make any engineer smile. Yiqian's fully automated rolling door bending line, straight out of Taiwan's finest industrial engineering. Watch as raw steel coil feeds seamlessly into the line. No hesitation, no manual handling. The roll-forming stations progressively shape the metal, bend after precise bend, until that flat steel transforms into perfectly ribbed shutter panels. What makes this system special? Every curve, every fold is controlled by a PLC system, programmable logic that never has a bad day. Tolerances stay razor tight, production stays blazing fast. At the punching and cutting station, panels are trimmed to exact lengths automatically. No measuring tape, no guesswork. Just flawless consistency. Thousands of panels a shift. This is how the world's top manufacturers compete. Smart machines. Relentless precision.